Hello, everybody. My name is Tobi Majekodunmi, and I'm a mechanical engineering student at the University of Maryland, Baltimore County. Today, I'll be discussing the work I did in the Atomistic Simulation and Energy Research Group under the mentorship of Dr. Majekodunmi and PhD student Alina Lapotin to develop a heat flux sensor. To begin with the context of my work, energy storage is crucial to the transition from the use of fossil fuels to renewable energy. And my team is leveraging the principles of heat transfer to develop a cost-effective energy storage device for use on an electric grid scale, known as thermal energy grid storage, or TEGS. TEGS uses collected electricity to heat up graphite, and that thermal energy is conserved through use of insulation. And once the energy is needed, it is converted back into electricity using thermal photovoltaic cells, or TPVs for short, which use similar principles to solar cells to convert heat into electricity. To measure how effectively the TPV cells convert thermal energy into electricity, you need to know the power output of the cell and the excess heat emitted by the cell. You can measure the power output through electrical contact, but to measure the heat emitted by the cell, you need a heat flux sensor, which measures the heat that passes through an area. While there are commercially available heat flux sensors, those options carry too high of a thermal resistance and cause the TPV's temperature to rise, which in turn decreases its efficiency. My responsibility has been to develop a heat flux sensor with a low thermal resistance. To accomplish this, we are utilizing the Seebeck effect, which is the voltage that results from the temperature difference between 2 points on a material. In the example depicted here, as the heater heats up the top surface of the copper and the bottom is kept cool, a voltage can be measured between the two surfaces proportional to the copper's Seebeck coefficient, S. We initially sought to make a heat flux sensor using direct bond copper, or DBC. DBC is made of two thin pieces of copper directly bonded to a ceramic. Aluminum nitride was chosen as the ceramic for its thermal conductivity and presumably high Seebeck coefficient. We observed that the voltage signal was too noisy to make accurate measurements, and it was then that we learned that aluminum nitride is a piezoelectric ceramic, a material that outputs a voltage when you apply pressure to it. And as you can see, the magnitude of the voltage caused by the piezoelectric effects drowns out the other voltage readings. During those immense voltage spikes, I was applying a frequent intermittent force to the piece of DBC. And we believe that the DBC's fabrication process may induce a constant state of stress on the aluminum nitride that results in the noise that we're seeing. While troubleshooting DBC, we conducted an experiment to confirm our tools are capable of measuring Seebeck voltages. We chose steel because of its high thermal resistance that would enable one portion of the steel to drastically increase in temperature while the other portions remain cool. As expected, we were able to achieve up to a 60-degree temperature difference and read voltage signals of up to 260 microvolts. Additionally, by tracking the temperature difference, we were able to determine our steel's Seebeck coefficient, 5.4 microvolts per Kelvin, which is within an order of magnitude of the value we found in literature. We are currently testing silicon as a potential heat flux sensor. This metalloid has a high Seebeck coefficient of 440 microvolts per Kelvin, as well as a high thermal conductivity. Although silicon is promising, it also has photoelectric properties, meaning that when it is exposed to light, it will output a voltage. Therefore, we must plate both sides of the silicon with gold to absorb any incoming light. The gold will also act as a surface we can bond our electrical connections to. Following that, we will use a manufactured heat flux sensor to develop an equation that converts the Seebeck voltages measured from silicon to heat flux values. And finally, after the silicon heat flux sensor is complete, we will test it in the black body cavity emitter to simulate the TEGS applications. I would like to thank my graduate mentor, Alina Lapotin, my faculty mentor, Dr. Ashegun Henry, and the other graduate students who helped me this summer, Colin Kelsow and Kyle Buznitsky. I would also like to thank my MSRP coordinators, Dr. Noel Wakefield and Maria Cervantes Gonzalez. Thank you all for listening.